Yeah, we are live.
Okay, then just give me a second. Is my screen visible?
Yes, it is visible.
Okay. Shall I start?
Yeah,
Okay. Good evening, everyone. Thanks for joining us for the day 5 session of the Data Structures and Algorithms Bootcamp. In this session, we will get started with tree data structures, where I will be covering a binary tree and binary search tree specifically, and you will be given a basic intuition on what you need to follow for all these. Also, I will be doing some live hands-on interview questions for my part, where I will be both writing some code and whiteboarding it. So make sure to follow them up and make appropriate notes. So let's get started. So before we jump into trees, let's start with a little bit of computer science. Data structures are simply a way for us to store and hold our data, just like I have mentioned before in my previous session. So that sounds a bit too simple, but it's true. So every data structure tends to have methods for inserting, removing, and finding an element in an array. So different data structures come up with unique pros and cons and unique time complexities. If you have any familiarity with any programming language, you already know about one data structure, array, or let's say list, specifically in Python. So now let's go back to the trees. So trees are specifically a non-linear data structure. So whatever data structures we have studied before, like arrays or list or list, these are all non-linear data structure. So trees are non-linear data structure. So this specifically means that unlike some other data structures like arrays or stacks, tree has no set start or end. So basically tree stores all the data as nodes. So the first node that is put into a tree is called a root. And this node can have child nodes that can only be accessed by first accessing the root node. So that the second node can then have its own children and so onwards. So the tree is storing all of the data in a hierarchical manner. This means that if we want to go to a child node, we first have to go through the root and then to the parent and continue until we finally reach our desired node. So a very great example of a tree data structure is the file system on our computer. So our personal computer has got its own root of the entire file system. Documents and desktop are its children, which makes them both siblings, like brothers and sister. But specifically in computer science, we call them as sibling. Then they can have their own children all the way down to the college assignment folder, which is empty and has no children at all, making it a leaf. So to get to any folder, you have to start at your PC, then to your desktop, and then you can access your folder, your desired folder, and whatever you have stored in there. Another example of tree data structure is the document object model in HTML. So the root of the body and every tag you add in the body can have its own children and so on. A great thing about trees is its time complexity. Inserting, removing, and finding a value in a tree all have logarithmic time complexities. This means that if you have a tree with a very high quantity of data, the task of traversing the tree would only increase at a smaller rate every time. And this is what makes the tree quite efficient in implementation as well as approach. So this is very useful if you are thinking about the possibilities of scaling your website or application to be usable by thousands or even millions of people. So let me start off with a general introduction to myself. I know that it's redundant now because most of you know me, but that's the beauty of it. So my name is Harsh, and I'm a software engineer intern at QXF2 and a technical content reviewer at Geeks for Geeks. I am currently working as a research attaché at Center of Innovation and Biodesign, and I work in the field of data modeling, machine learning, web development, and algorithmic development. I also like to do some competitive coding, and I'm a mentor at various open source events like Hacking Codes, PSOC, and Student Coding. So if you want to catch me up, you can do so on LinkedIn, Reddit, or GitHub, or even Instagram. So let's get started. So in a computer science, a tree is a very general and powerful data structure that resembles upper real tree. So I guess majority of you guys have seen a real tree somewhere around you. So a tree data structure actually quite resembles it. So it consists of an ordered set of linked nodes in a connected graph, in which each node has at most one parent node and zero or more children nodes with a specific order. So if you want to imagine a tree, you can imagine a family with relationships from all generation, like grandparents, parents, children, siblings, and all. So we commonly organize family trees hierarchically, and this is how the tree data structures work as well. So there are many real world application of trees. For example, PDF, like the portable document format, it is a tree based format. It has got a root node followed by a catalog node followed by a pages node, which has several child nodes. So producers, consumers, they often used a balanced tree representation to store a document in a memory. So most databases, like, they make use of trees to store data on their drive. They also make use of some other type of trees, like specifically T trees, so that they can store all their data in the memory. Social networking is like the current buzzword in the computer science research. It goes without saying that connections or relationships, they are very naturally modeled using graph, but trees are specifically used to represent or identify some more specific phenomena. So a tree is a widely used abstract data type, and it is basically a data structure implementing this ADT. So it simulates a basic hierarchical tree structure with a root value and subtree of children with a parent node represented as a set of linked nodes. So let's check out an example and see how a tree looks like. And let me just erase it once. So this is how the tree will look like, and what are the various terminologies in a tree data structure. Okay, that's good. So if you have got any other doubts, you can just put it right in the YouTube live chat. So let's just get started. So I will make a very basic tree. So let me just call it 2, 3, 6, okay, 7, 9, 5, okay, and lastly 11. So this is what hello, am I audible?
Yes, Harshit, audible. Please go
Okay,
on.
okay. Yeah, sure. Thank you. There were some net issues from my side. Sorry for that. Am I audible right now?
Yeah, Harshit, you are audible.
Yeah, okay. So this is what we call as a basic tree. So a tree is a finite set of one or more nodes. So basically we have multiple nodes here, like 2, or we have got 3, we have got 6 and all. So these are the basic finite set of one or more nodes. And this is what we call as a tree. So there is one specifically designated node that we call as a root. So here specifically 2 is our root element. So let me just mark it right here. So 2 is our root element, and basically all the other nodes can be called as its children. So then we have got the concept of branches. So branch is basically like the link between the parent and its child. So right now 2 is a parent and it has got its own 2 child. So this is 3 and 6, and the link that is connecting both of them, it is called a branch. So right now there is another thing that is called as a leaf. So a node with no children is called a leaf. So if I take the example, then 11 is called as a leaf, 5 is called as a leaf, 7 is called as a leaf, and 9 is called as a leaf. So basically leaf can be called as a node with specifically no children. And finally we have got subtrees. So subtree is a basic like subset of a tree that itself is a tree. So if I take a specific subtree, then 379 is a subtree. So 3 is the child of 2, and it has got its own left child and right child. So this is what we call as a left child, LC. Let's call it LC. And this is what we call as a right child. Let's call it RC. So 379 is a specific subtree. So subtree can be basically defined as a subset of a tree that itself is a tree. Then we have got the degree of nodes. So the number of subtrees of a node is called the degree of the node. So let's say if I'm talking about 3, then its degree is 1 because it has only got one subtree inside it, and so forth. So, and finally, we have got levels. So let me just talk about levels. So level of a node is defined by letting the root at the level 1. So the element 2 is present at level 1. So let me just keep it as level 1. We have got the other two elements at level 2. So this is what we call as level 2. And finally, all these elements are present at level 3. Sorry for mishmashing this whole up. So these are the most important terminologies and the concepts that you need to know about the tree data structure. So let me just clean it up once. Yes. So let me just make a more beautiful diagram. So this is what we call as A. Then we have got B and C. We have then got D and E. And here we have got F and G. So if you are making notes, just make note of this diagram. So this is what we call it as level 1. So A is our root node, B and C are its children, and it is present at level 2. So these are our level 2. And finally we have, and finally we have got all these elements at level 3. So A is a root element up here. So A is our root. B and C are the children, while D, E, F, G are called leaf because they don't have their own children. And the connection between all these nodes is called as a branch. So these are the most important terminologies that you need to know about the tree data structure. So let's move ahead. So I've covered up this slide. Okay. So now we have covered up the basic terminologies behind the tree data structure. So let us check out some of the most popular versions of the basic tree data structure. And the ones that we will be covering up in this session will be binary tree and binary search tree. So binary trees are the most common type of the tree used in computer science. So basically a binary tree is a tree in which every node has at most 2 children. So it is as simple as that. So if we have got a root node, then that root node can have only 2 children. The rest of the 2 children can have their own children, and it should not exceed the boundary of 2. And this is how the basic binary tree is formed. So in a binary tree, we extend the concept of linked list data structure to structure containing nodes with more than one self-referenced field. So a binary tree is made of nodes where each node contains a left reference and a right reference and a data element. So the topmost node in the tree is called the root. Every node, excluding the root element, in a tree is connected by a direct edge from exactly one other node. And this node is called a parent. On the other hand, each node can be connected to an arbitrary number of nodes called children. So nodes with no children are called leaves or external nodes. Nodes which are not leaves are called as internal nodes, and nodes with the same parent are called siblings. So you can perform all sort of operations on a binary tree like insertion, deletion, updation, and all. So let's check out a binary tree. So first of all, I will be drawing up on how a binary tree looks like. So yes, so let's draw a simple binary tree. So at the root element, we have got 6. It has got 2 children, let's say 2 and 8. And finally, 2 has got its own child 1, and 8 has got 7 and let's say 5. Okay, so this is what we call as a binary tree. So just like I mentioned before, it is a root element. This is the branch that is connecting them. These two are the children of 6, and they can be called as a sibling. So they have a relationship between them. And this specific thing is called as the left subtree. So what we specifically call it like this. Sorry for this. So I can call it as left subtree LST. And this is what we call up as the right subtree, basically RST. So every node has got its own left child and a right child. If a specific node has no children, then it is called as a leaf node. But if any node has got its own children, then it is called as an internal node. Now, when we talk about binary trees, then we have got our own sort of different types of binary trees that we can have. So let me just show it up right here. So the first binary tree that we can have is a skewed binary tree. So skewed binary tree looks something like this: A, B, C, and D. So basically we have got a root node, and this root node has got all the elements in a specific left subtree or the right subtree. So this is what we call as a skewed binary tree. Then we have got a strict binary tree as well, and this one is quite interesting. So strict binary tree looks something like this. So we have got a root node, we have got elements B and element C, then we have got D and D. So now you might ask, what is the difference between a regular binary tree and a strict binary tree? So binary tree actually strictly enforces two principles. The first principle is that no node should have its own children. And if it has got its own children, then it can have at maximum 2 children only. So here you can see that B has got 2 children and C has got no children at all. So it is strictly following the principles of binary tree. And this is why we call it as a strict binary tree. So basically it is like strict STR binary tree. This is what we call as a skewed binary tree, SKW. Yeah. So this is the difference between a skewed binary tree and a strict binary tree. Lastly, we have got something that is known as a complete binary tree, and it is very simple. So basically all the elements will have got its own children, and it looks something like this. So A, B, C, D. So this is what we call as a complete binary tree, because every element has got its own children, and lastly the leaf nodes have got no children at all. So this is what we call as a complete binary tree. So with this we have covered up the very basic concept of the binary trees. So why don't we like simply code out a simple binary tree and let's check it out. So this is the basic code for a binary tree. So what I have done here is that I have created up a class and I have initialized a constructor up here. So basically we have got our own a self-referencing assignment for the left node, a self-referencing assignment for the right node, and finally a data element. So if we can visualize this in form of a linked list, so how does this look like? So let's check that out right as well. Yeah. Okay, so let's check that out in terms of a linked list. So when we talk about linked list, then it will look something like this. So basically, this will be the root node. It has got 2 address nodes and it has got 1 data node. So let's say I'm storing the data 2 here, and it has got 2 address node. So this is the address. This one is the address node for the left subtree, and this one is the address node of the right subtree. So this address node of the left subtree will be referencing the element that is present in the left subtree. So like, let's say I'm keeping it as like 3, while this particular data point, like the memory address, will be referencing to the node present in the right subtree. So it will be looking something like this. So basically now I can create more 2 address points. This can be referenced again to some other data point like this. This can be referenced again to some other data point. Let's say 7. And if possible, we can just keep it as null if there is no other children of this particular specific node, or we can just reference a data point for this part. So this is how tree data structures can actually be modeled using the purpose of linked list. You can also do the same using arrays, but the thing is that arrays will be quite complex to implement the tree data structure. So it is always preferred for you to implement all the tree-based data structures, especially binary tree and binary search tree, using linked list only. So we are making use of the same here. So right now at the left node, we are not keeping any data point. We are just keeping it as none. Same at the right, for the right subtree, we are keeping it as none because we are not inserting any node. For the data point, for the data assignment, we are keeping the data. And finally, we are printing it. So we are just including a root node and we are just printing it. So it is doing just this simple operation. So if I'm printing it, then it is showing 10. So if I want to input any more elements to this binary tree, I need to perform some separate insertion, search or deletion operation according to that. So that will be covering up in the later part of the session. So let's move next to tree traversal. So basically a tree traversal is simply an algorithm that allows us to visit each node in a tree once and only once. And this can be done in multiple ways, but always have several steps in common. So the first step is for each node in the tree, you must first determine whether a left subtree or node exists or not. And if it exists, then you should recursively traverse it. So I guess you already know the concept of recursion that was pretty much covered up in the second day of the session. So we regularly make use of recursion for all our traversals and all our search operations, and even insertion and deletion operation. Next, you have to determine whether a right subtree or node exists or not. If so, you have to recursively traverse it again. And finally, you have to handle the node itself. So these steps can be done in different orders, and the order in which these steps are completed determine in which order the node of the tree are traversed. So let's check out some of the examples for our purpose right here. So let me just go back to the whiteboard again. So guys, if you want to understand the tree data structures, just follow this part properly, because this is one of the most popular college question as well, a gate question as well, and some interview questions as well. So check out this example properly because it will help you to understand the tree traversal with much more depth. So if we can just take a look at the first tree traversal we have right here. So it is like pre-order, in order, and the post order. So specifically, what difference do all these tree traversals make right here? So we will try to discuss that out right now. So let me just take the pre-order traversal first. So I'm building a specific binary tree. So this is the root A, B, C. Okay, that's cool. D. Okay, D is not visible that much, but we will consider that. And finally, F. So we now need to print all the elements in this specific tree. And there can be multiple orders in which we can print this tree. So one order can be like A, B, C, D, E, F. So there are n number of ways in which we can print this tree. So one order can be like So we can print this tree specifically in many orders. The first order can be like A, B, C, D, E, F. Some other order can be like D, E, F, B, C, A. Then some other order might be like D, B, E, A, C, F. So there are n number of ways in which we can print this same binary tree in multiple different manners. But we need to standardize in what way can we actually traverse the whole tree. So for that purpose only, we are making use of specifically three tree traversals. The first one is pre-order, the next one is in order, my favorite one, and the last one is post order. And if you're solving any sort of like an algorithmic question which involves binary tree, you specifically need to see on which traversal you can use for your own purpose. Generally, in order tree traversal is used for the majority of the times because it gives us a sorted list of elements if you are performing the operation on a binary search tree. So we will be covering up that later. So how can we traverse this tree using pre-order? So if we can just visualize this whole operation using pre-order, then first we will be taking up this element. So let's just print this. So first we will be taking up A. Next, we will be taking up B. Okay, let's just print this. Next, we will take up D. Okay. And now what we will do is that we will switch to E right here. So we can do this for E. Then we can completely switch back to C. So this one is C right here. So we can print C, and finally we can do F. So this is our complete order of tree traversal. So first we will go to the element A, then to B, then to D, then E, finally C, and then F. So this is what we call as the pre-order tree traversal. So in pre-order tree traversal, you have to first process the root R. Then you need to traverse the left subtree of the R in the pre-order format. So basically, like first I will be jumping from the root tree, from the root node to the left subtree. Then I will be traversing this whole left subtree in the pre-order itself. And then I will be like jumping to the right subtree and traversing it. So this is how pre-order tree traversal actually works out. So let me just take another example, a very simple one. So 1, 2, 3, 4. Okay, so this one is a very simple one. Try to comment out in the live chat on what can be the pre-order tree traversal for this. So till then, I will just remove all this stuff right here. So just think out for a moment. So what you need to do is that first you need to jump onto the root node, then you need to go to the left subtree. You need to traverse it according to the pre-order traversal, and then you need to jump to the right subtree. So if I just give out the answer, then the answer will be something like this. First 1, 2, 4, and then 3. So this is how easy pre-order tree traversal is. So next we will be covering up in order tree traversal, and it is my most favorite tree traversal right here. So let me make another binary tree. So first A, B, C, don't know what that happened. Okay, and finally F. So how are we going to determine on what will be the tree traversal for an in order traversal procedure? So in order is also quite similar. It is also quite simple, but it starts right from the leaf nodes. So right here, we need to first go to the right subtree, sorry, the left subtree, like the extreme left leaf element present in the left subtree. So right here, the D is the element. So first we will be printing out D. So D will be the first element that will be printed out. Next, we need to switch to the right subtree. So E will be the element. And then we need to go back to the, sorry, I did it wrong. So from D, we need to jump back to the root element. So the root element for all these children is B. So then we will be doing it for the B part. And then we will be going to the right subtree. So it will be D, B, E. So once the left subtree has been completely traversed, we will be again going back to this root element, which is A, and we will be printing out that again. Next, we need to go to the leaf element of the right subtree, which is F, and that will also be printed out. So F has also been printed out. And lastly, we will do that for the C. So how is this entire tree traversal working out? So let me just give an example for this. So like right here, first we need to go to the extreme element present in the left subtree, which has got no children. So D is the element for us. We will print that out. Next, we will go to the root element, which is B. Next to E, which is present in the right subtree. Then we will jump over to the root element A. And then we can perform the same traversal on the right subtree as well. So F will be the element that will be printed out. And lastly, C will be printed out. So you can take a few seconds more and you can think on what can be the in-order tree traversal for this tree. So in-order tree traversal is quite handy. So for majority of the times, binary search tree or B tree, they specifically like make use of in-order tree traversal for all their operations. So it is quite handy and it is quite of an important concept that you should know about. So if I take for this thing, then the answer for this would be 4. Then the answer would be 2, 1, 3. So it will be like linearly going in this manner. So this is what we call as an in-order tree traversal. And lastly, we have got the post-order tree traversal. And this one is also quite interesting for our purpose. So let me just draw the subtree back. the whole tree back again. Yashika, is my voice breaking today?
No, Harsh, it's all right.
Okay.
Yes.
So we have got another tree up here, and now we need to give the post-order tree traversal up here for this. So in the post-order tree traversal method, the left subtree is visited first, then the right subtree, and at last the current node is processed. So like in this example, what we will do is that we will first print out D. So let me just do that right here. So first D will be printed out, then we will visit E. So right here, E, and then we will go back to the root node. So DEB, and again we will not be going to the main root node right now. What we will do is that we will now print out this, so F, then we can jump back to the root node C, and finally we can implement the main root node, that is A. So this is the answer for this. So how is this operation actually playing out? So basically, like since the A has a left subtree, the post order traversal method is applied recursively on the left subtree of A, which is basically like this is the left subtree of A. So then when the left subtree of A is completely processed, the post order traversal method is recursively applied on the right subtree, which is, so this is basically the right subtree. And if the right subtree is completely processed, then the current node A is also processed. So if you just take a look at this example, then what do you think can be the post order traversal for this thing? So just think that out right now, and if possible, try to put that answer right in the chat section. So the answer for this would be like, first 4 will be processed, and since it has got no sibling, so basically the root node 2 has got no right subtree, we can jump directly to the root node here. So it will be 2. We will not be jumping directly to the root node. We can jump back to the right subtree here, which is 3, and finally 1. So this is the entire concept of in order, pre-order, post-order, and this is how exactly the things play out. So if I erase all this, okay. So now let's move ahead with the next concept of this session, which is binary search tree. So we are now taking a look at the binary search tree, which is a particular type of binary tree that provides an efficient way of storing data that allows particular items to be found as quickly as possible. So as we have already discussed before, many computer science applications involve searching for a particular item in a collection of data. And if the data is stored as an unsorted array or list, then to find the item in question, so one obviously has to check each entry in turn until the correct one is found, or the collection is completely exhausted. So on an average, if there are n items, then we have to do like n divided by 2 checks. And in the worst case, all n items will have to be checked. So this is what we do in the linear search operation. So if the collection is large, such as all items accessible by the internet, that will take too much time. So we also saw that if the items are sorted before sorting the array, one can perform binary search, which only requires log2 base n checks in the average and the worst case. However, that involves an overhead of sorting the array in the first place, or maintaining a sorted array if the items are inserted or deleted over time. So the idea here is that with the help of binary tree, we can speed up the storing and the search process without needing to maintain a sorted array. The solution to our search problem is to store the collection of data to be searched using a binary tree in such a way that searching for a particular item takes minimal effort. So the underlying idea behind binary search tree is very simple. At each tree node, we want the value of that node to either tell us that we have found the required item or tell us which of its 2 subtrees we should search for it. So for the moment, we shall assume that all items in the data collection are distinct with different search keys. So each possible node value occurs at most once, but we shall see later that it is easy to relax this assumption. So as you can probably guess, a binary search tree is a binary tree. So there is a very little distinction between them, but the key difference is that a binary search tree only allows you to store nodes with a lesser value on the left side and the nodes with a greater value on the right. So let me just take an example before moving ahead. So right now, for majority of my examples, I was making use of binary search tree only, but let me formally take an example for that. So let me take the root node to be 9. I have got the left children as 7 and the right one as 12. Then 7 has got its own left child, which is basically like 5, and it has got its own right child, which is basically 8. So 12 has also got its left child, which is 11, and its right child, which is 17. So what are the things that you can see up right here? So basically you can see that there is a root element, which is 9. So 7 is the left child of the root element, and 7 is lesser than 9. So it is occupying this position, which is of the left subtree. 12 is another child of 9. So basically you can see that 12 is greater than 9. So it is occupying the position of the right subtree. And you can see the same things here now. So 11 and 17. So 11 is lesser than 12. So it is occupying the left subtree. 17 is greater than 12. So it is occupying the right subtree. So here as well, we can see that 5 is lesser than 7. So it is occupying the left subtree, while 8 is greater than 7. So it is occupying the right subtree. So now you can see that all the elements that are present in the left subtree, they are all lesser than the root element. So 7, 5, 8, they are all lesser than the root element. While in the other case, 11, 17, 12, they are already greater than the root element. So this is exactly how binary search tree can speeden up our whole search process. So let me say that I want to find this specific element, like let's say I want to find 11. So in a linear search, we have to go on each and every element. And in the worst case, we will get a time complexity of O of n. But what about binary search tree? So in a binary search tree, we can just take an element like, let's say X. We will see if that element X is greater than the root element or not. If it is greater than the root element, we will go to the right subtree. If it is lesser than the root element, then we can go to the left subtree. And this is exactly how the whole operation will be playing out. So we can recursively follow this approach, and we can finally get to our element in the minimum possible time. And this is the reason why binary search tree is so much popular among computer engineers and developers, because it allows you to store your data and query it without needing that much of the data operations to be performed. So now that we have got a basic intuition, let's move next. So like any other data structure, binary search tree is a dynamic abstract data type. So, and it has got some fixed operations to perform. Like since you have checked out stack, you can see that you can perform pushing, you can perform popping out. So in binary search tree as well, you can perform all these operations, which is basically searching an element, inserting an element, and finally deleting an element. So let's check each one of them out with some examples. So the first one is finding an element. So let me just clear this up, this whole mess. So I guess you already have an idea on how we can search for an element, but I will just make this a bit more intuitive for you. Okay. So let's take an element 10. Okay. It has got 7. This one has got 15. Okay. It has got let's say 5, and it has got 9. Okay. So same for 15. Let's say it has got its left subtree element as 12, and this one, let's keep it like 17. So as you can see, the elements that are present on the left subtree, they are all lesser than the root element. The elements that are present on the right subtree, they are all greater than the root element. Now we need to find one specific element, which is 9. So let me just take X is equal to 9. So what will be the first operation that we will perform? So we will first take up the root element, and we will see if this root element is greater than 9 or not. So we found out that 10 is greater than 9. So since 10 is greater than 9, so this element should be like, it is quite possible that it is present on the right subtree, sorry, the left subtree. So this is the left subtree. We will perform the same operation recursively now. So from 10, we will jump back to the 7, and we can see if 7 is greater than 9 or not. So we found out that 7 is actually lesser than 9. So since 7 is lesser than 9, it is quite plausible that 9 will be present on the right subtree. So we jump from 7 to 9. And right here, we have got the element. We will check if this element is equal to 9 or not. Yes, it is equal. It like the element that we wanted to find is neither greater nor lesser than this element. It is perfectly equal. So yes, we have find out the particular element. So this is how easy it is to compute the like get a search query on a binary search tree. So now that you have understood it, let's move to some other complex operations, which is basically insertion and deletion. Like these are the most important ones. Okay, so now let's do some insertion and the deletion operation. So let me again make a binary search tree. So 10, 7 again, 15 again, 5, 9. For 15, we have got 12, okay. And for this one, we have got 17. Okay, this one looks cool. So now we need to find out, right, that we need to insert an element which can be basically 6. So let's say we want to insert an element that is 6. So how do we do that? So again, we have to follow up a recursive approach because following this will be quite handy, and we can like perform this operation almost repeatedly. So whenever an element is to be inserted, we have to first locate its proper location. Then we start searching from the root node. And if the data is less than the key value, we will search for the empty location in the right subtree and insert the data. Otherwise, we will search for the empty location in the right subtree and insert the data. So how are we exactly doing this? So first we will check if 6 is equal to 10 or not. So it is not equal. And we found out that 6 is actually lesser than 10. So this element can only be inserted in the left subtree. We will completely eliminate this part. We will not be traversing upon this. So 6 is lesser than 10. So let's move over this. Now we will jump from 10 to 7. And now we will try to find if 6 is greater than 7 or lesser than 7. So turns out we found out that 6 is actually lesser than 7. So again, it will go to the right subtree. So basically we land upon 5, and 5 is a leaf node. It has got its no children. So now we find out that 5 is actually lesser than 6. So once we take it into a perspective of linked list, we can see like this. So basically 5 has got 2 address points, and both of them are null. So it is not referencing to some other data point. So since 6 is greater than 5 and 5 has got its no children, so it will happily invite 6 to be its own child on the right subtree. So what it will do is that it will take the location of 6 and it will input it right here. And with this, 6 will become one of the child of 5. And this is how exactly we can insert any element in a binary search tree. So first we need out to find out the correct location of that particular element. We need to traverse the correct parts. And once we found out that we have reached to a particular leaf node, then we can just simply insert it by referencing the address point of that particular node. So this is how we insert an element to any binary search tree. And lastly, we have got the deletion operation. And let me tell you, deletion operation is actually the most complex of all operations that you can do on binary search tree. So let me just clean it up. Okay, it's fine. Let me take a pencil and let me again make a binary tree. And this time it will be a bit more complex. So 11, 7, 15, okay. 7 has got 2 more, 5, and 9, okay. It has got 3, it has got 6, 9 has got 8, it has got 10, okay, and 15 has got 13, it has got 20, okay. So 13 has got its own like 12, let's say, or 14, and 20 has got its own 18. No, it's not 25, let's say, okay. And one more, 18 as well. So sorry for this whole mashup. I expect that you can understand the basic intuition. So right now, while you are deleting a node from a binary search tree, actually there are three cases that you should consider. The first case is that the node that you're trying to delete is a leaf node. So if I can just take all the leaf nodes here, then 3, 6, 8, 10, 12, 14, 18, 25, these all are like leaf node. So the first scenario involves a leaf node which does not have a left or a right child. So in this case, we will need to remove the node by assigning null to it. So how do we do that? So basically, like, let's say if I want to delete 3 right here, I want to just delete 3. I don't like this element. So basically, like, if you can see that 5 has got 2 nodes, which is like 2 address points, which is for 3. So this one is basically referencing 3, and the second one is basically referencing 6. So now I want to delete 3. So it is basically a very easy operation. What we can just do is that we can dereference this assignment and we can assign null to it. So I will just dereference it and I will assign null to it. So it will not be basically pointing to any data element. And in this way, 3 can be completely deleted from the binary search tree. Now we have got a second scenario. The second scenario involves a leaf node which does not have a left or no, sorry, which involves a node that has a left or a right child. So like right now we can see that we have deleted 3 and we want to delete 5 also, but there is a catch. 5 has got a child and this child is 6. So we cannot easily delete 5, because if we delete 5 in the same way that we did in the first scenario, we will be losing out 6 as well. So to do that, we need to perform another operation. What we exactly need to do is that we will first find out 5. Next, what we will do is that we will see if it has got a child, if on the left subtree or the right subtree. And next, what we will do is that we can simply link this to the 7. So 6 will be occupying the position of the left subtree of 7, and the 5 will be completely deleted. So this is exactly a linked list operation. So if possible, what you can do is that you can try this operation out on a pen and a paper, and you can try to visualize this. And this will help you in better understanding of what we are trying to do here. So basically, we are grabbing up the data point of 6. We are assigning this to the, like, let's see if I'm taking it right here. So 7, okay. So this data point is referencing 5. So what we will do is that we will dereference the address point of 5 and we will address the reference point of 6. And this is how exactly we will be deleting of 5 from this complete binary search tree. So this is how we exactly handle both the scenarios. The first scenario is that we are trying to delete a leaf node. The second scenario is that we are trying to delete a node that has got either a left subtree or a right subtree. And now we have got an Avengers level threat. And this Avengers level threat is that we have to delete a node like this node that has got both a left subtree and a right subtree. So like in this third scenario is a bit more complex because it involves a node with both left and right children. So once you find the node to be removed, find the minimum node from its right subtree. So this is exactly what you need to find out. So if I take out the minimum node from the right subtree, then it is 18. So yes, we found out the minimum node from the right subtree. Next, what you can do is that you can update the value of the node with the key of the minimum node from its right subtree. With this action, you can like actually replace the key of the node, which means it is effectively removed. Now you have only 2 nodes in the tree with the same key, which cannot happen. Thus, you need to remove the minimum node from the right subtree since you moved it to the place of the removed node. And finally, you can just return it so that the updated node reference to its parent. So if I'm doing it on a practical level, then what I can do is that I can just dereference this assignment point and I can place 18 directly up here. So 20 will be basically deleted, 18 will be occupying the point, and it will have its own like the right child, which is 25. So this is exactly how we can delete a node which has got its own left and a right child as well. So you just need to find out the minimum element in the right subtree. You just need to place it in the exact correct position that it deserves, and then you can finally dereference the assignment. So this is exactly how you can search, insert, or delete any particular node on a binary search tree. It will be a bit more complex. There might be some issues in understanding, but once you start doing all these operations on a pen and a paper, You can easily implement this using some concepts of linked list and all. So try to give it a shot, and I will also be sharing some of my own code with you so that you can take a look at that and you can try to implement it at your own level. So with this, we have finally reached the interview questions. So let's try to crack some of the interview questions that are present on lead code. So let's get them cracking one by one. Okay, so basically, let's check out our first question. So the first question states that given the root node of a binary search tree and a value, you need to find the node in the BST that the node's value equals the given value. So if I just take the question here, so it is basically a tree right here, 42713. We have to find a value 2, and it should return this subtree. So this is a very easy question. What you can do right here is that I will just remove all that. Okay, so I have almost removed all this. So let me just do one stuff. Let me just take the example right here, 42713. Okay, so 4, 2, 7, okay, 1, and 3. Okay, so now we have a binary tree. We have to find out an element 2, and it should return this particular subtree. So exactly how are we going to do that? So we will do this recursively. First, we will go to the root node. Okay, we will try to see if 4 is greater than 2 or lesser than 2, or it is equal to 2. So we found out that 4 is actually greater than 2. So we will do this operation recursively, but on the left subtree. So let me just go back to the left subtree here. Now that we will land upon the left child, which is 2, we will check if 2 is equal to 2 or lesser than 2 or greater than 2. Turns out that 2 is actually equal to 2. So 2 is actually equal to 2. And then we will return this whole subtree in the answer. So it is a very easy question. You just need to apply some of the concepts of recursion in this. So let me just implement it right here. So in the leads code environment, they have actually implemented the whole binary search tree right from the scratch. So we don't need to implement it for our own purpose. We just need to fill up this function, and we can do this all operation. So we can first check if the root is none. So basically, I'm handling an edge test case. So basically, an edge test case means that if they are giving you some undesired input, then you have to handle that as well. So let's say if some of the test cases contain a tree that has got no elements, or simply the root doesn't exist. So what are you going to do in that case? So it might cause an error. So for handling that edge test case, I'm using this if statement. So if root is none, I will just simply return nothing. Okay, yeah, then I will take out the root value. So basically this is the value point. So I will take up the root value. I will check if my value that I'm trying to find it out right here, it is basically equal to the root element or not. If it is equal, then I will simply return the root element. Okay, next I will basically check if that root element is greater than, if that root element is lesser than the element we are trying to find or not. So in that case, what we can do is that we can reference the constructor, we can search for the BST. So I am calling the same function again right here so that this whole operation can be performed recursively. So I will take it up root right. So basically, like if that element is lesser than, if the root element is lesser than the element we are trying to find, we will switch back to the right subtree right here. So for this purpose, I will be like passing on the right subtree root, and I will be passing on the value. Okay. And lastly, if root value is greater than the value, so what I will do is that I will again call this function. So root left. Okay. And finally value. And for handling one last edge test case, let's say we are not getting any tree from the compiler. So I will just return this thing. So, okay, we have done. Let's try to run this code and see if we have got any sort of errors. Okay, so it has been accepted. Let me just submit this code and see what we get at the end. Okay, so runtime is 84 milliseconds and it is like faster than 48.11% of Python 3 online submissions. So yes, it is quite good, but let's check this parameter up right here. So right here, you can like see, okay, So basically, like you can see with the Python solution, we are getting an 84 milliseconds timeline. But for a similar logic that I implemented in C++ almost a few months back, like almost 2 months back, I got the same thing in 72 milliseconds. So even if the logic is same, what you can do is that you can try switching up languages to see in which complexity you can get the better solution at. So this is what exactly you can do. So I guess most of you have understood this question. If you have not, just let me know in the YouTube live chat and I will be resolving all that out in the Q&A session. So, okay, we have completed this. So let's move next with the second question of our agenda, which is insert into a binary search tree. And it is a medium level question. So let's try to brainstorm upon this a bit. So we have got another tree, 42713, and we have to insert a value. So let's go back to the whiteboarding thing again. Okay. Okay, so 4, 2, 7, okay, 1, and a 3. And we need to insert an element 5. So first, what we will be doing is that we will first check if this element, yes, there might be an edge test case here. So note that there may be multiple ways for the insertion as long as the tree remains BST after insertion. And it is guaranteed that the new value does not exist in the original BST. So this is actually a relief for us. So let's say if I'm trying to insert an element 4 and 4 is already present in BST. So I need to make one more edge case to handle that. So for this question, we don't exactly need to do that part. We can just take up an element and insert it on the pre-assumption that this element does not exist in the BST. So again, we will be doing the same stuff. We will check if 5 is greater than 4 or not. So turns out 5 is greater than 4. Okay, so we will not be going into this part. What we will do is going to this part here. So now from 4, we will jump back to the 7. We will check if 7 is greater than 5 or not. So turns out that 7 is actually greater than 5. So from here, we will jump to the left subtree. But since it has got its no children, what we will do is that we will simply insert 5 here. So this is how exactly we are doing. And I guess I have explained this a bit before a few minutes back. So let's try to implement the code for that as well. So again, they have implemented majority part of the code for us. So we exactly don't need to do all this stuff together. So I will just create a nested thing here. Okay. So first I will handle the edge test case. So if node is none, I will simply return the tree node, which is basically this one, the root node. So tree node with the val. Okay. Next, I will be handling if value is actually greater than the node val. Okay. So we will like node left. So basically we will be going to the left subtree and we will do a recursive operation here, right here. So insert node and it will be like node dot left. Okay. And if both of these operations are not satisfied, then we will just go to the right subtree and we can perform the same operation there in a recursive manner. Okay. So with this, I will just simply return the node. And lastly, I will return insert node here. Okay, so let's run this code to see if we have got any sort of syntactical errors. Okay, so there is one silly error. I just need to fix that. Okay. Okay, we have got some sort of an error right here. Let's try to debug this. Okay, so where is it? This one is correct. Okay, so error is here. So the value should be actually lesser than the root value. So basically we can just go back right here. So we can check that the left subtree should be always lesser than the root element and the right subtree is always greater than the root element. So we will just fix this simple bug. We can again run this code. Yes, it has been accepted. We can submit this up. Okay, and this is faster than almost 89.08% of the Python 3 online submissions. which is quite amazing. So yes, we have cracked 2 lead questions, and remember that majority of the binary search tree questions, they are either related to inserting a node or they are related to searching a node. So if you can crack these 2 questions comfortably with multiple different variations, you can simply get comfortable with any question that is related to binary search tree. So let me just go to the last question, and this one is my personal favorite. And this question is related to inverting a binary tree. And this question has got an interesting background. So he's a Max Howell. He's a creator of a software that is Homebrew. And Max Howell managed to get an interview with Google. And Google said that almost 90% of the engineers use the softwares you wrote, but since you cannot invert a binary tree, we cannot hire you. So this is exactly the thing that is happening in the software industry right now. So there are many great developers, but they don't have an intricate understanding of data structures and algorithm. So this is exactly why you need to know about them if you want to get cracking at some interviews at FANG-based companies. So again, we have this question. Let's go to it right now. And this one is a very intuitive question. So basically, we have got this binary search tree. So let's draw it up right here, 4271369. Okay, looks like some phone number. So this one will be the last question of our session. So 4, 2, 7, 1, 3, 6, 9. So how are we exactly going to solve this? So if we can just go back to the question, the resultant output we will go is 4729631, which is exactly the inverse. So 4, 7, 2, 9, I guess it is correct. 9631, sorry. Okay, so this is exactly a mirror image. So if you have studied physics, you can understand this thing. So this is exactly a mirror image that we are trying to form here. So this operation can be simply done recursively. What we exactly need to do is that we just need to exchange both the left subtree and the right subtree nodes. And we need to perform this operation recursively so that we can finally manage to get an inverted tree. So how do we exactly do that? So what we can do at first is that we can exchange both of the address point. So 7 will occupy the position of 2 and 2 will be occupying the position of 7. And we can do the same thing for all their elements as well in a recursive manner. So I guess I can do this right here. Okay, yeah. So first, let me manage to handle the edge case. That is our prime priority right now. Okay. Next, what we are going to do is that we will just swap it up right here. In Python, you can do this in just one line. Okay. So once we have done that, we will reference it and we can pass off this function itself recursively. So now I will pass off this one as left. So basically what is this doing is here, like once we swapped all these two, so basically this same operation will be done with these two elements as well. So this is why exactly we are making use of the concept of recursion here. So self.invert tree, okay, root. So once we have done that, we can simply go one step back and, sorry, not here. And we can write return root. So let's run the code to see if there are some sort of a syntactical errors. So yes, it has been accepted. Let's just submit this. Okay, so basically it is faster than 84.24 of the Python online submissions. And if you take a look at this, then I have applied the same logic a few months back with C++, and the basic runtime is 0 milliseconds. So this is how exactly C++ is quite efficient if you are doing any sort of a data structure or an algorithms question. So C++ is taking up very less space complexity. It is taking up only 8.5 MBs of data. Python is quite fast compared to other submissions, but it is still taking a lot of runtime and it is taking a lot of memory as well. So if you are choosing up a language, try to take these parameters at the edge because they are going to play an important role while you're submitting at some online contest or even directly in the interviews. So with this, we have finally came to the end of the session. If you have got any questions or doubts or queries that you want to get resolved, so you can ask that right now in the YouTube live chat. If you want to get your doubt clarified directly by me, you can find me at the rate Harsh Casper, or you can just drop me a mail so that I can resolve your doubt right there. So thank you for joining in for this session on tree data structures, and I hope every one of you enjoyed it. So you can start sharing your questions and we will be happy to resolve that out. Yashika, can we start taking up questions? Okay, so I can see Anudita has a question on like how to calculate the height of a tree. So let me just open the whiteboard back again and share my screen. Just give me a few seconds. Okay, so if you guys have any other doubts, you can just put it right in the chat section. I will first be resolving this doubt on how to calculate the height of a tree. I don't know why it is taking up this much time. Yashika, is my screen visible?
Yes, it's visible.
Okay, so
Yes.
if we can, oh gosh. So basically, like we have a very simple formula for this purpose. So if there are n number of nodes in a binary tree, so it can have at least 2h plus 1. So basically, h is the height of a tree. So it can have at least 2h plus 1 number of nodes, or at maximum, it can have 2 power h plus 1 minus 1. So where h is the height of the tree. So basically, you can derive of the number of nodes present in that. So yes, it is back online. So let me just clear it up. Okay, so this very basic formula is that if n is the number of nodes, then the least number of nodes it can have is 2h plus 1, where h is basically the height. And it is basically the height. And n is equal to 2 power h minus h plus 1 minus 1. So this one is the minimum number of nodes that can be present in a tree, and this one is basically the maximum number of nodes that can be present in a tree. Yashika, do we have any other question?
Yes, Harsh. Let me read.
Yeah.
Okay. So Preeti is asking, I have a question like if we have to count number, minimum swap of number in an array, how can we do that?
Minimum swap of an array for what purpose actually?
she has not mentioned, she has just written, I have a question, like if we have to count number, minimum swap of number in an array, how can we do that? Preeti, can you explain what actually want you ask?
So if this operation is to like do this for the purpose of like, let me just close this, stop sharing my screen. So basically, if we can do this operation like to sort the array, so what we can do is that we can simply visualize this problem using a graph. So we will have n nodes and we will have edges, and it will be directed from node I to node j. And this is how we can like check if that element is present at the ith index, and it must be present at the jth index in the sorted array. So tomorrow we have a session for this part specifically on the graph data structures. So I can specifically take up that, and I can take up this question.
Okay, so another question is, one thing I wanted to ask was, I am planning to use Python for competitive coding, feels more comfortable. Is that a disadvantage?
So basically the thing is that majority of the people, what they do is that they make use of Python. So because of the inbuilt libraries and modules that it provides you. But in the shorter run, it will be quite beneficial for you. Even I use Python for general purpose programming and sometimes for competitive coding. But let's say you want to progress further and you want to solve some complex algorithmic problems, then in that case, Python will not be the most preferred language for your case. So try to switch to some other language like C++ or Java for your purpose. So because you cannot rely on Python because of its inefficient time and space complexity. So as you can see, like in the three questions, what I did was that I implemented the same logic in C++ and Python, and I got drastically two different results. So with C++, my time complexity and space complexity was a bit reduced. And it was quite specific to the language that we are like working on. So you can probably make a switch to C++ or Java. You can check out some of the inbuilt things that are present in those languages. Like in C++, we have got standard template libraries, while in Java, we have got big integer classes. So with that, you can just simplify your operations, and you can do a lot of stuff there.
So Harsh, I have a question. Is it a good idea to like pick Python for interview questions and for C++?
Okay, so the thing is that in interviews, basically they will give us two options. The first option is that like they will give you a question. So like this question can be, let me just take up a question basically. Like let's say I have an array, and this array consists of only ones and zeros. So it entirely composes of only ones and zeros, and you have to like modify the array in a given way, in such a way like the ones are stacked up on the right side of the array while zeros are stacked up on the left side of the array. So this is one very popular interview question. So they will give you two options. The first option will be to go to a whiteboard and to solve this question and to basically speak out. So while you are solving this question, try to speak out as much as possible. Try to take the hints from the interviewer, because this is one of the most underrated skills. Because the interviewer will be explaining the whole problem just once, and you have to grasp the problem. And if you have not got it, or if you have not understood it, just ask that interviewer on on what specific case that this problem applies to. So the interviewer will be more than happy to solve your query, and you can explain your mind. So let's say I'm trying to solve this problem, I'm using a specific algorithm. So try to speak out, try to visualize this whole problem, and try to present it before the interviewer. So the interviewer is basically trying to take a look at your mindset and to see on how deep you can think or how you can handle the edge cases. So first you will be solving it on a whiteboard. So once you have solved it on a whiteboard, you can basically write a pseudocode for that, and you have optionally a chance to come on a compiler and basically like compile it. So that is just like an optional thing, but majority of the people, what they do is that they go to the whiteboard, they solve this, and they basically come back to the compiler and they make use of that. So in that case, Python is a bit more preferred because of its simplicity and its similarity to the pseudocode. But once you are adept in one particular language, you will be basically sticking to that for the longer run.
Thanks for the insight, Harsh, by the way. Thanks so much.
So any more questions? If anyone wants to ask, please write on the chat box. Okay, so Harsh, everyone is praising you. Great session. Loved the session.
And I was actually sweating the whole time. Like I had the urge to go back to the YouTube live chat and see if they have got any doubts, because in the middle there was some network disturbance, but hopefully that was not denting the whole part out.
Yes, yes. It was just, I think once only some network issue was there. Otherwise, everything was very smooth.
Okay then.
Yes.
So tomorrow we are going to have a session on graphs. So me and
Okay.
Vijaya will be taking this session. So try to specifically attend it, because we will not be delving much into the coding, because doing code on graph data structures is very hard. So we will be explaining you some of the most basic stuff. And in graph data structures, we basically have multiple algorithms. Like we have got Kruskal's algorithm, Prim's algorithm, Jastra algorithm. And all these algorithms are like very important for your interview point of purpose, because these are related to core problem solving. So try to attend that. We will give you a theoretical introduction as well as a very basic coding introduction on how you can get started with the graph data structure. So tree, graph, dynamic programming, these three should be like the main swords in your arsenal if you're going for any technical interview or if you're going for any coding competition, because these are the data structures and algorithms that they will be asking you the most. So try to keep your concepts cleared in that so that you can get the best out of the whole thing.
Okay, then Harsh, there is no more questions. So I think we should wrap up the session. Anything else you want to say?
Not today.
Okay.
Yeah.
Okay, then thank you, Harsh. Thank you everyone for attending the session. So I think tomorrow is the most important session. Try to attend this. It's a very important session for you. So we'll meet tomorrow at 5 p.m. Okay. Thank you, Harsh, and thank you everyone.